Hello learners, welcome to session 4 of Unit 2 in the course Introduction to Abstract Algebra. In this session 4, we are looking at partitioning of a set. I am your course instructor and my name is Mukaila Tasmani. By the end of this session, you should be able to define and describe a partition. Also, partition a set into equivalent classes to be able to generate other sets from a given set using relation. Determine the domain and codomain of relations. Good. So, definition of partitioning of a set. A partition P of a set is a collection of an empty set x1 up to xn such that xi intersection xj is not equals to empty set for all I not equals to j, and the union of all x must be equals to x. Okay, so that's what the partitioning of a set is. Let's similar to symbol be an equivalent relation on a set x, and also let small x be a member of the big X. Then what can we say? Then you can say that equivalent class of x is equals to y is a member of x. Here for y which relates to x, and this is called the equivalent class of x. An equivalent class or equivalent relation gives rise to a partition through equivalent classes. So once you have equivalent relation, that gives rise to partitioning, and that is through equivalent classes. Okay. Also, whenever partition of a set exists, there is some natural underlying equivalence relation. Once the partition of set exists, then that natural underlying equivalent relation also exists. So theorem, given an equivalence relation on a set x, the equivalent classes of x form a partition of x, and I think you agree with me. Conversely, if p equals xi is a partition of set x, then there is an equivalence relation on x with equivalence classes xi. So this is the proof, and the proof is self-explanatory. Go through the proof in order for us to shorten the video. So the proof continues here. You can see it's very simple and self-explanatory. In session 3, example 19, which you did it as an assignment. So if we let p, q, and r as well as s be integers, where q and s are all non-zero, and define p on q relates r on s, if p of s equals qr, then the relation is reflexive, symmetric, or transitive. Okay, so in this equivalent relation, the two pairs of integers p, q, that's p and q, and r and s are in the same equivalent classes when they reduce to the same fraction in its lowest term. So if you put in numbers, you simplify further, you realize that they were in the same classes. Even when we reduce them by cancellation, they find out that they are in the same classes. Good. In session 3, exam 21, we showed that if f and g are differentiable functions and r, we define an equivalent relation on such functions by letting f of x relate to g of x if and only if f prime of x equals g prime of x. So we show that the relation is reflexive, symmetric, and transitive, that is an equivalence relation. To show that the relation is transitive, we suppose that f of x relates to g of x, and we also suppose that g of x relates to h of x. In this equivalent relation, the two functions f of x and g of x are in the same partition when they differ by a constant. Remember, when we integrate the function f prime of x, we get f of x plus the constant c. So we're having c1 and c2 over there. There are more examples in your course material. You can find out more examples in your course material, which are very simple, self-explanatory. Thank you.